Yes, Dora. Today I'll be exploring how we can enhance safety and efficiency in autonomous vehicles through machine learning. Join me as we delve into the techniques, applications, and future directions of this transformative technology. Okay, this is the table of content like introduction, review, and all. So what's the research question? What are the current challenges and advancements in applying machine learning to autonomous vehicle perception? And how can these insights contribute to enhancing safety and efficiency in autonomous vehicles? Um, so we will be finding the answer for that question throughout the project. And as an introduction, autonomous vehicles, also known as self-driving cars, represent a revolutionary shift in how we perceive and interact with transportation. So imagine a world where vehicles navigate busy streets and highways without human intervention, where commuting becomes safer, more efficient, and environmentally friendly. This vision is becoming a reality thanks to advancements in technology, particularly in artificial intelligence and sensor systems. So, as we delve into the fascinating history of autonomous vehicles, let's begin by exploring Leonardo da Vinci's visionary concept from 1478. Leonardo da Vinci's 1478 sketch of an automatic car with its primitive autopilot steering system laid the foundation of today's autonomous vehicles. And in the 1920s, Francis P. Houdini unveiled the Lincoln Wonder, it's known as the American Wonder as well, an early attempt at autonomous vehicle technology, which utilized radio controlled mechanisms to navigate the streets remotely. Powered by electric motors, it could steer and accelerate based on radio signals received. And in the 1930s, Norman Bell showcased automated guided cars at the 1939 World's Fair. Invention in highways automated through electromagnetic fields in the roadway, laying the foundation for autonomous transportation. But as I know, this is just a sketch. He didn't implement this. And in the 1916s, James L. Adams initiated the development of the Stanford cart at Stanford University, which later evolved into the slider, showcasing dynamic movements and autonomy in navigation tasks. Carnegie Mellon University's NavLab project, led by Professor Red Whitaker, further researched in autonomous vehicles, producing multiple generation capable of navigating real-world environments. And in the early 2000s, significant strides were made in autonomous vehicle technology, leading to the development of pioneering prototypes. Among them were vehicles like Tesla Autopilot and Volkswagen Stanley and Carnegie Mellon Jr., which competed and excelled in the DARPA Grand Challenges, marking significant milestones in the journey towards autonomous driving. And now let's dive into the automation levels of autonomous cars. The Society of Automotive Engineers has described 6 categories assessing vehicle autonomy from level 0 to level 5. Level 0 means no automation, the human driver can control the vehicle at all times. Level 1 means drive assistance, the vehicle can control some aspects of driving, such as steering or braking, but the human driver must still be alert and ready to take over. And level 2 means partial automation. The vehicle can control most aspects of driving, but the human driver must still be ready to take over in certain situations, such as when the vehicle encounters an unexpected obstacle. Level 3 means conditional automation. The vehicle can drive itself in most situations, but the human driver must be available to take over at all times. Level 4 means high automation. The vehicle can drive itself in most situations without human input, but it may require human interventions in rare circumstances. Lastly, level 5, full automation. The vehicle can drive itself in all situations without any human input. Now let's begin by discussing the different paradigms of machine learning that are crucial for autonomous vehicles. These paradigms include supervised learning, unsupervised learning, and reinforcement learning. Supervised learning in autonomous vehicles entails training algorithms on labeled datasets to recognize objects and lane boundaries from input data, crucial for tasks like object recognition and lane keeping. Unsupervised learning in autonomous vehicles leverages unlabeled data to identify patterns and structures, crucial for tasks like anomaly detection and scene understanding, enhancing perception capabilities. Reinforcement learning in autonomous vehicles enables decision making based on feedback, enhancing navigation in complex traffic scenarios by learning from rewards or penalties during operation. Now, moving on to the challenges and limitations faced by autonomous vehicles, let's delve into some key points. Please note that these are related to machine learning. Concepts, massive data requirements, time and computational resources, challenge in human interaction recognition, limitations in responding to human intuition, and concerns about anatomy and trust. Now let's talk about the sensor technologies in autonomous vehicles. In autonomous vehicles, sensors are crucial for perceiving and locating the vehicle's environment, enabling real-time decision making. We employ two main types of sensors. First one is exteroceptive sensors. That means here you can say LiDAR, which utilizes laser beams for high resolution 3D mapping, radar, which uses radio waves for detecting objects, especially in adverse weather, camera, which captures images for object detection and lane detection, ultrasonic, which emits sound waves for short range obstacle detection, and the second one is proprioceptive sensors such as GPS, which provides global positioning data for navigation, IMU, which measures forces, angular rates, and magnetic fields for motion tracking, and encoders convert shaft position into signals for determining relative position. So these sensors work together to provide comprehensive data for autonomous driving, ensuring safety and reliability in various driving conditions. Now we're going to talk about the vehicle perception. Under that, we can see sensors, perception, planning, and control are there. So vehicle perception relies on a variety of sensors like LiDAR, radar, cameras, ultrasonic sensors, GPS, and all to gather environmental data. This data is processed using machine learning algorithms to identify objects, estimate their positions, and understand the vehicle's surroundings. The output of the perception stage informs the planning and control systems, helping determine the vehicle's trajectory and adjust parameters for safe navigation. Overall, these stages enable autonomous vehicles to perceive, plan, and control their movements, ensuring safe and efficient driving. Now let's talk about the sensor fusion. So sensor fusion combines data from multiple sensors like cameras, LiDARs, and radar to enhance the perception of autonomous vehicles, increasing system reliability. The process involves sensing where diverse sensors capture information about the vehicle's environment, followed by data processing, where raw sensor data is integrated and analyzed to create a clear understanding of the surroundings. Then machine learning algorithms play a crucial role in sensor fusion by detecting, segmenting, classifying, and monitoring objects in the environment, ensuring safe navigation. Once the vehicle gathers and processes information, it plans its movements, making decisions about actions like lane changes and turns. Finally, the control module executes the planned route by sending precise instructions to the vehicle's components, ensuring safe navigation. Overall, sensor fusion enables autonomous vehicles to navigate safely and confidently in various environments. Now let's deep dive into the sensor fusion techniques. Here you can see the first one is 3D object detection using sensor fusion. That means combining LiDAR sensors and cameras in autonomous vehicles, optimize perception by utilizing cameras for visual details and LiDAR for precise 3D object detection with neural networks, enhancing accuracy through individual sensor signal processing before fusion. The second one is sensor fusion for occupancy grid mapping. Here also, it combines cameras and LiDAR data to enhance accuracy by identifying occupied, free, and unknown areas through a grid-based system with cameras capturing 2D visual information and LiDAR providing precise 3D data. Then the sensor fusion for moving object detection and tracking. Here, detecting and tracking moving objects is vital for safe autonomous driving, relying on a blend of sensor data for accurate perception. So these sensor fusion techniques demonstrate the integration of diverse sensor data to enhance perception, navigation, and object detection in autonomous vehicles, paving the way for smart and more reliable autonomous driving system. Now let's talk about the cybersecurity of these autonomous vehicles. So securing automotive control systems, including electronic control systems and in-vehicle systems, is crucial in automotive cybersecurity to prevent unauthorized access and manipulation of critical vehicle functions. Additionally, safeguarding autonomous driving components like sensors and mobile apps from cyber attacks is essential to maintain system safety and reliability. Ensuring the security of V2X communication network is vital to prevent disruptions and maintain data integrity in autonomous driving environments. Conducting comprehensive risk assessment helps identify and mitigate potential vulnerabilities in autonomous vehicle systems, allowing proactive measures to strengthen cybersecurity defenses. So, by prioritizing these measures, autonomous vehicles manufacturers can effectively mitigate the cyber threats and ensure the safety and reliability of their vehicles in an increasingly digital world. Now, let's delve into the challenges faced by autonomous vehicles, such as safety and reliability concerns, regulatory and legal issues, scalability and infrastructure adaptation, data security and privacy concerns, and all. Now, so the next one is future directions. So here you can see like distributed and edge computing architectures, module designers for easy integration, and integration of advanced communication technologies like 5G and adaptive learning for continuous improvement. And we can increase the redundancy in critical sensors for the fault tolerance, and incorporating decentralized decision making, human centric design, and even though I haven't mentioned here emotional intelligence, incorporating emotional intelligence comes into my mind. So that's those are will come under the future directions. And so today we discussed a lot of about self-driving cars. We looked at how they evolved over time and how they use cool technologies like sensors and computers to drive um, safely, but there are still some challenges to figure out, like making sure they are safe and people feel comfortable with them. So in the future they will get even better with new technology, but we need to work together to make sure they are safe and helpful for everyone.